Alright, so we are halfway through a proof, and we did one direction, and now we have to do the other direction. But thankfully I can state everything that we want and need to show. So for the reverse direction, suppose one goes to N, goes to G, goes to H, goes to 1, where we have phi and psi, is a short exact sequence with a section S, and I'm just going to write this up here, such that psi composed with S is the identity on H. Okay, so then this means that this short exact sequence is split. So I claim that G is equal to H semi-direct product with N. So remember what that means. That means that G is equal to H times N. We also need H and N to be subgroups of G and N to be normal. And we need the intersection of H and N to be trivial. And that's it? Yeah. Okay, so we need H and N to be subgroups of G, and we need N to be normal in G. Now, if we're given this short exact sequence here, we don't really know. We need N and H to be in G in some sense, but here these are just N and G and H are just groups that were given to us. We G could be Sn, and then N could be like a dihedral group. That could entirely be impossible, but the point is that these groups need to have nothing to do with each other. So does it really make sense to have H and N as subgroups of G? And this is where we're going to get kind of into the gray area of what it means for two sets to be equal versus two sets to be isomorphic. What we're going to have is, instead of having H, really what we're going to prove is not so much that literally G is the semi-direct product of H and N, but it's more so that there is a subgroup of G, where there is some subgroup H prime of G and some normal subgroup N prime of G, such that G is the semi-direct product of H prime with N prime, and such that H prime is isomorphic to H and N prime is isomorphic to N. But because having to do with H prime and N prime would be so much more detail than is really necessary for our understanding of what's really going on in this proof, we're just going to call them H and N. And so I'm going to specify this right now. So we can identify N with a normal subgroup of G via phi. And this is because N is the image of phi. Right, N is the image of phi. Well, that's if this is inclusion. Do I want to say that N is isomorphic to the image of phi? Yes, I do. And why is that? That's because of the group homomorphism theorems. Phi here, because this is a semi-direct... Wait. This map is injective. Yes, yes. Okay, so by the fundamental theorem of group homomorphisms, N is, so this map phi is injective, and so if we, remember, if we mod out this, if we mod out by the kernel, we get an isomorphism onto the image. So if we mod out by the kernel, so modding out by the kernel is modding out by the identity subgroup, but that's just, whenever you mod out by the identity, you're just left with what you started with, which is N. And then the image of N is just, or the image of N under this map is just the image of phi. And so N is isomorphic to the image of phi, but the image of phi is equal to the kernel of psi because this is an exact sequence, it's exact at G. But remember, this is the kernel of a group homomorphism, and so this is normal in G. So even though N has nothing to, really has nothing to do set-wise, the elements of N have nothing to do with the elements of G, N happens to be isomorphic to something, which we can prove is normal in G. And likewise, we can identify H with a subgroup of G because H well, right, the image of G is precisely, or the image of psi is precisely H. And so right, No. Here we need more information, and I think this is really going to start to get at the heart of why we need this to be a split short exact sequence. What we do is we actually associate with a, we don't use psi to our help, we use S. Because, let's see here, so S goes from H to G, and psi of S is the identity. So, so we can, because what happens is if we restrict S to its image, so this, the image of S, I'm trying to think, okay. So here's what we do. We take psi and we restrict it to the image of S. And this should yield a bijection or rather it should be an isomorphism. Yields an isomorphism between H and a subgroup of G. Or rather, the subgroup image of S which is going to be a subgroup of G. Because let's think about this. So we know that psi composed with S is the identity. So if we go this way, we get the identity. All we need is so if psi of S is the identity, then if psi is psi of S is the identity. So if S is a bijection, since psi of S is the identity, certainly anything that gets to here is going to have to go. If you send something through this composition, it's not going to get to psi unless it's in the image of S. If you can see what I mean there. And so the identity of H is not just equal to psi of S, but it's also equal to psi restricted to the image of S. And then from there, all we need is that if S happens to be both injective and what else do we need? No, because then S has an inverse, which is the. What we need then is we need S of psi restricted. We need S composed with psi restricted to the image of S to be the identity on the image of S. And so if you take something that's in the image of S and you send it through psi, then it will go to something in H, and then that in turn will obviously go to something in the image of psi. I'm actually at this point, I'm going to cut this off, this discussion. I think it's pretty clear that that you can use S to embed H as a subgroup of G, but I'm just kind of not. I don't have all the details fully worked out, and it shouldn't be hard to do. I just am going to keep just the wheels are going to keep turning, and I'm not going to make any real progress, and I'm not going to be able to show you a proof that's concise enough for how minor of a detail it is. So anyways, so it is true that you can get H being isomorphic to a subgroup of G, and you use S to prove that. Right, because it's obviously the image of S is a subgroup, and you just prove that that's isomorphic. Okay, so anyways, so we need G to be equal to Hn, and we need H intersected with N to be trivial. So let's start with the first one. So to prove G is H times N, let G be in G, and we want to consider any element of N. But wait a minute. So what we're going to do, we're going to let G be an element of G, and we're going to let H be psi of G, and of course this is going to be an element of capital H. So if we can write G using this element of H and multiplying it by some element of N, then we'll be good. So then look at this element SH inverse times G. So this would be a good candidate. Why? Do I have this right? Well, let's just keep going here. So then, this is an element of phi of n, so the image of phi, if and only if, now the image of phi is the kernel of psi, so that's sh inverse g is in the kernel of psi, and that's if and only if psi of sh inverse g is equal to the identity in, let's see here, psi is going from there. So this is the identity in G. But this is a group homomorphism. So this is if and only if psi of S of H inverse you know what? I'm going to use parentheses instead here so that the notation isn't super messy. If and only if psi sh inverse psi of g is equal to eg, and this is if and only if. Okay, what's psi of s? Psi of s is just the identity. And so if we bring this inverse inside here, which we can do because this is a group homomorphism. So there, we do need S to be a group homomorphism. So, so when we bring that inverse inside, we get H inverse times psi of G equals the identity here. If and only if, okay, what's psi of G? Psi of G is H. So H inverse H equals EG, and then if and only if, obviously, EG equals EG. Thus, SH inverse G is in the image of phi. Which is identified, remember the image of phi is isomorphic to n. So then G, we can write it as SH times SH inverse G, because we're just multiplying by SH and SH inverse. But SH is in a place where, what is that place? SH should be an H. Right, because SH is in the subgroup of G which we associate with H. So we're just going to say that this is in H times, and then remember, this is in that subgroup that's we associate with N, and so this is N. So, thus, G is contained in H dot N. And hence, but H dot N is obviously going to be a subgroup of G, so in particular it's a subset, and so hence G is equal to H times N. Alright? Finally, for the last part, suppose that G is in H intersect N. Remember here we're trying to prove that H intersect N is trivial, so we want to prove that G is the identity. So what is H? H is the image of S? Right. H is associated with the image of S, and N is associated with the image of phi. So G is phi of X and S of H for some X in N and H in H. Again, these are in G. So then H is psi of S of H, because psi of S is the identity map on H. But S of h is phi of x, so this is psi of phi of x. But remember, this is a short exact sequence. So anything in psi of phi of x, anything in here will go to its image, which is the kernel here, and so it'll get sent to 0. So anything that starts here, you send it through twice and it dies. It becomes the identity. Typically, algebraists use death to denote something becoming the identity. So it's kind of dark, but it can also be kind of humorous. But not right now because I'm sort of rushing to finish this. So this is EH. So G equals so G equals S of EH equals EG. So then H intersect N equals identity, and hence G is the semidirect product of H and N. And there we go. I know I got a little stuck over in here, and I'm sorry about that for not working out the details, but it's a very small fact, and you can work out the details if you want, or you can just believe me that it's fine and it works. But anyways, this completes our proof of this proposition. And so we have a link between short exact sequences with splittings, or short exact sequences which are split, and semidirect products.